Good morning, everyone. We come to lecture 17. So today we will continue on the topic of Raman spectroscopy. So Raman spectroscopy and group theory. Okay, let's briefly review what we learned last time. So last time we learned that if you have a material with a certain polarizability tensor, then when you apply electric field, you will induce a dipole, and this dipole will irradiate. Then you have the scatter light. Okay, so let's consider electric field equal to a certain polarization, okay, with a frequency omega, and then this alpha, this hat means it is a tensor. It is a tensor, okay, will be affected by a phonon mode. Will be affected by a phonon mode. You can say Q. So it will be the same as the original one plus some correction term, basically the Taylor expansion. Okay, so this is at equilibrium position, zero displacement, and with the Q. And then this Q is basically just cosine big omega. Okay, big omega. Okay, so this is the phonon frequency. This is photon frequency. So with that, we can just write it. We can just write it out. Just write it out. Okay. This should be just a vector. Okay, so let me just write this as an incident. Okay, incident. Then you just do a Taylor expansion. And then you just copy this. I mean, we already did this last time. So here, just briefly review it. Copy. Plus. Okay, so this is the inelastic scattering. So we're going to focus on this one. This will be equal to 1/2 Q E incident cosine omega plus T plus omega minus T. Okay. So this is the Raman scattering. Okay. So basically, this is the anti-Stokes and the Stokes Raman. Okay. So here, this is what we call the Raman tensor. Raman tensor. You can call this this is the Raman tensor. I mean, you can include the Q or not including the Q. I don't think it matters too much. Okay, so this Q basically denotes the magnitude of the oscillation. Okay, so this P is proportional to the scatter electric field. Okay, to the scatter electric field. So the detection. Okay, so and then this is proportional to delta incident. Okay, so you're going to have a certain detection. Okay, so let E be the unit polarization vector of the incident light. Incident light. In and then copy and let E you just say detection then of the unit vector the detection unit vector. Okay, so then the detection intensity is I equal to this one detection dot the dot this thing dot and square. And usually you need to add the complex conjugate in case you're using circularly polarized light. If you don't use circular polarized light, it doesn't matter. Okay, proportional. Okay. Okay. So then let's continue to write it out. This will be proportional to E detection dot this thing. Okay, dot this thing. And then will be square root. And of course, eventually, if you don't care for this intensity of the incident light, you can just simply change this. The zeros out of the bracket. Yeah, you're right. Incident. Yes. 0. Okay. Okay. So that is what we're going to consider in this lecture. Okay. So this one is the Raman tensor. I think some paper, my old paper said this one is the Raman tensor. I actually don't know what is the original. I mean, I have a paper that say this one is the Raman tensor, but this Q is insignificant. Okay, with the Q, without the Q, but the symmetry part comes from this. So you can call this the Raman tensor or this the Raman tensor. I forgot what is the original definition with the Q or without Q. But it doesn't matter for our symmetry consideration. Okay, so let me simply just use R. Hey, what happened? Okay. Oh no. Oh yeah. Okay, let's rewrite it. I don't know what happened. Okay, so this is all proportional. Proportional to E detection. incident. Okay, so we just call this R then. Okay, just say Raman tensor. Okay. Okay, so this determines the Raman selection rule. So this determines the Raman selection rule. So R follows the symmetry of the vibration mode. The vibration mode. So each phonon will have the corresponding Raman tensor. Okay, and that corresponds to the symmetry of the vibrational mode. Okay, so we're going to consider some simple cases, how to apply the group theory to get the Raman selection rules. Okay, so first let's go back to this paper that we considered last time. So this is a APL paper that I published some years ago with the Professor Ruihi. So it's on the stacking dependent shear mode in trilayer graphene. Okay, so last time we already talked about this by using those cartoons. Okay, but we didn't really use the group theory. So today we're going to consider the Raman selection rules by using the group theory. Okay, so let's consider just ABA. Yeah, let's consider ABA trilayer graphene, and the symmetry group is D3H. D3H, and these are the representation of the four Raman modes. So D3H. Okay, so let's go to D3H. So this is D3H. You go to the website here and then click D3H. Okay, then you see the character table. Okay, so we're going to use this table. Okay, so let's consider the shear mode. So let's write it down. Okay, ABA trilayer graphene, and then the group is D3H. Okay, so for D3H, so we will consider the lower shear mode and then the higher shear mode. Higher shear. And then you also have the maybe put it here. Lower shear mode. Okay, so you also have the breathing mode. The lower breathing mode. Okay, so the lower shear mode, let's write it down. Is Z double prime, and then this is Z prime. Lower breathing mode is A1 prime. Higher breathing mode is A2 prime. Okay, so we write it down. So let's consider E double prime here. Okay, let's consider E double prime. Okay, E double prime. E double prime is this one. Okay, so this is E double prime. Okay, look at these functions that transform according to E double prime. So these are the rotational modes, and we're not considering this. And this is the tensor element, x, y, x, z, y, z. Okay, So this basically shows the form of the Raman tensor, because any tensor will transform according to this. Okay, it's a two-dimensional representation. So not all the elements of the tensor is involved. Only these two elements are involved. Okay, so let's consider Raman tensor. Okay, so let's say R. The Raman tensor equal to they're totally generally they're totally 9 elements. XZ, YX, YY, YZ. So you know this is related to d alpha over dq, right? So alpha is a symmetric tensor, right? Polarizability tensor is a symmetric tensor. Okay, so this Raman tensor is a symmetric tensor. I mean, a symmetric tensor after you do the derivative is still symmetric. Okay, so there are totally 6 in the independent element. Okay, so we only need to consider 6 of them. Okay, 6 of them. For the E double prime mode, you can see that only XZ and YZ are there. All the other elements are 0. Okay, only these two elements transform like this. I mean, you have other elements, but the other elements transform in a different way, in different representation. So that means for this particular phonon mode, you only have these two elements. Okay, so you go back and then pick it up here. So the R for the E double prime, okay, is only XZ and YZ. So where is XZ? XZ is here, YZ is here. Okay, so all the elements are 0. So you can write it here, XZ, YZ. Okay, you can write it here. So these are just two independent group elements, and people usually, for convenience, they simply just use A, B, C, D. What symbol I use? You just use use C and D. Okay, just use C and D to represent it. C, D. Okay, so basically, C and D are just constant. So this is the form of the Raman tensor. Okay, you can get it easily. So what does it mean? What does it mean? Okay, so then you just go to here. We only need to consider this part. Okay, so for the I, E3 mode is proportional to this. So then you just put this tensor here. Copy. And then this is just E in, E detected. Okay. I mean, you can easily tell if E in equal to EX, then you have equal to 1, 0, 0. Then here you need to have a 1 to make it C. Okay, and if E equal to Y, then you just get this. Then this will be D. Okay. So that means the detection is you have X Z. This will be X. This will be Z. Will be proportional to the C square. Similarly, this is YZ. This will be D. Okay. I for all other polarization combination, such as E double prime XY is 0, XX is 0. All of them are 0. That means you shine the light. Let's say this is your sample. Okay, you have X, Y, Z. So if you shine the light, let me use this as a Y extent. Okay. See there. Okay. Then the light will be something like this. Okay, my drawing is not very good, but you get the idea. Okay, EX. Then the Raman will go like the other way. Maybe I use let me use a green color then. Okay. Okay, get the idea. My drawing is not very accurate. Okay. Okay, then the scatter light, the Raman will be like this. Okay. So the Raman will be like this. So you shine the X polarized light, the Raman will be Z polarized. Because this is what it does get. Okay. The same, you shine the X or Y, either way is fine. You get a Raman propagating with a Z polarization. Because the wave vector of light is perpendicular to the polarization. So you know that the scatter light will be in plane. So that's why in our geometry, if you put the objective here, shine the light and collect the same light, you are not going to get anything. Okay, so this mode, so this mode is Raman inactive. in the XY or XX detection scheme. For X and X, sometimes people call it horizontal VV, like, and XY people call it HV, like H means horizontal, V means vertical. Just terminology, okay? HV, those are the names for the detection geometry. That means you excite with X, you detect X. Excite with Y, you detect Y. Okay, I mean all the other way. If you detect Y, excite with Y, detect with Y. And some people just write HVV or HV, just terminology. So you know that for this E double prime mode, it is not going to be observable in our geometry. And you can see that this is the case. For ABA, for the shear mode E double prime, you can see that it's not there. Okay, it's absent. It's absent. Is it okay?
So it's because you detect from.
Yeah. It's just the reflection geometry that you use in our lab. One objective. You excite and detect in this with the same objective. So that's why you don't detect it. Okay. And in our experiment we didn't see it. Okay. And so although it is Raman active, but then in that particular detection geometry, we could not see it. Okay. Any questions? Okay, it's straightforward, right? And not very complicated. Okay, let's do a few more example and exercises to kind of get you more familiar with how to apply the group theory. Okay, let's get E prime. Okay, if you go to E prime, then is this mode. Okay, you can see that it has a vector XY. So that's why this mode is infrared active. Okay, and the dipole is in plane, XY in plane. Okay, the dipole is in plane. Okay, let's come to here. This is the tensor element. You have x squared minus y squared xy. Okay, so this is the finite element. Okay, so let's go back. Let's go back. And then we're going to get this higher shear mode. Okay, for the higher shear mode, what is the form of the Raman tensor? Okay, we just copy it like this. So let's forget about this part first. Okay. So this will be E prime. So how many elements are there? So you can see that here is x squared y squared xy. So you can see there will be x here. These are all 0. Okay, so this will be the form of the Raman tensor. You have all this. However, you can see that this is not just x and y. This is x squared minus y squared. So that means there will be some relationship between x and y. Okay, so let's write it like this. Let's write x plus y. Let's write it as x plus y plus. Okay, and then let's define minus. Okay, so let's define. So you can see that this one will be 1/2. Okay. And then this one minus. Okay. So this one.
The first ones.
Huh?
Or R minus is X is.
No? Okay. Yeah. Okay, my typo. So this one is not 0. Because in group theory, minus. So this one will be 0. And this one is not 0. Okay? This is allowed by group theory. So this one has x squared minus y squared xy. So this element is finite. Okay, so this one is finite. This one is finite. This one is 0. Okay, so that means this will be 1/2 this, and this will be negative 1/2. Okay, negative 1/2. So from there, you can deduce that they're negative of each other. Is that okay? Because group theory only tells us that this one is finite. That means this one is 0. Okay, so that means these two, x and y, they're not independent of each other, because their sum is 0. Okay, once you know their sum is 0, I mean, you can immediately get that they're negatives each other. Okay, is that okay? So the Raman form will be A, negative A, and B. Okay, so this will be the form of the Raman tensor. Is that okay? This one? Because group theory tells you that only these two elements are finite, all the others are 0. Only this combination transform like a E prime representation. The x squared plus y squared, this element will transform according to A1 prime. So this combination does not belong to this representation. Okay, so that's why in this Raman tensor it is 0. Is that okay? Any questions? Okay, so you can set this as 0. Then this is finite. I mean, once you set this 0, then you already know that these two will be opposite to each other. So the form of the Raman tensor only have two independent elements. Okay, so now let's consider E detection dot R E prime and incident. Okay, let's consider this. We can easily tell. Okay, so if you consider EX, then it will be 1, 1, 0. Okay, then you will have A and B. Okay, so this will be a certain combination of EX plus BY. Okay, And similarly, if you consider EY, then we just write the same thing. Zero, one, then it will be B and negative A. B and negative A. So that means if you're excited with X or Y, you're going to get a combination of X or Y. Okay, so that means if you let me copy this again. Okay, copy this. We don't have this. You're going to have what? So you're going to have a how can I represent it? Okay, I write it here. Okay, so you're going to have a combination. How can I write a combination? I don't know how to write it. Okay, so this will be the E. Okay, this will be the E scatter. The E scatter. Okay, you get the idea, right? Okay, it will be a combination of E and Y. Okay, so that means if you use X or XY, you get non-zero Raman signal. Okay, or you can say HH or HV is not going to be zero. However, if you get XY or YZ, you're going to get zero. I should not say equal to zero. Just become zero. Okay. Okay, become zero. So if you try here and detect here, then you're not going to see anything. But the X polarization will generate both X and Y component in the Raman. Is it okay? It's pretty simple. But here, there's one thing that's very interesting here. Suppose now you use circularly polarized light. Okay. Consider E incident equal to sigma plus. Okay. That means 1I. And then E detection equal to sigma, also sigma plus. Okay, then we'll get something interesting here. That is, of course, you need a zero here because the Z component is zero. One I zero. Wait. Yeah. Sorry, it's chaotic. Control. Okay, just write it like this. So you're going to use this. And then this one, you need to add the complex conjugate, okay? Because once you use complex number, the dot product will be you need to have a complex conjugate on the other side. Okay, so you're going to get 1i, and then here will be 1 negative I dot, no need for dot. Then let's get the answer. So this will be a plus b, bi minus ai, and then a plus b plus this one times this.
Minus the minus.
Uh,
Should be a plus I.
Yeah, you're right. Yeah. Yeah. Okay. Okay. So thank you for the correction.
I think the left vector should be row vector. Right one should be column vector.
Yeah, I know. I add the dot product then. Okay. 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 You know what I mean, right? I mean, if you want to write it that way, that's fine. Then this one is not a star. This one will be like a joint. Okay. Anyway, add the dot here. You know, it's just dot product. Okay. So because if you're writing another way, it just doesn't look very well. Okay. So will be a, and then minus bi plus a. No, minus a. Okay. Yeah, okay. Okay. Anyway, get 0. Okay. So let's continue. Let me just copy the whole thing. Okay. Okay, now consider the detection is the opposite. Negative. Okay, so then this one will be negative I. Then this will be negative. Then this will become positive. Positive. Okay, so then it will be this will be plus, and then it's just not 0. Okay, it's not 0. Anyway, I want to write it in the same page. Okay, so you get the idea. You get the idea. So what does it tell us? Okay, let me copy this thing again. What does it tell us? That means you shine the circularly polarized light. You're gonna get something like this. Let me see how I'm going to draw it. You get something like this. Okay, something like this. So this will be Yi. Let me say this is, I don't know what is right-handed or left-handed, but anyway, you just right-handed. And then you're gonna get something like this. And then it will be left-handed. So then it will be something like this. Okay, something like that. Okay. So this is a helicity dependent. Helicity dependent. Is okay. So you have a left and right-handed light. The Raman will flip the helicity of the light. Okay. The Raman can flip the helicity of the light. Okay, so now let's go to the breathing mode. Yeah. The breathing mode. The breathing mode is A1 prime. So what is A1 prime? A1 prime is here. A1 prime is this. Okay, this is the breathing mode A1 prime. So let's write it. Okay, so we'll have ABA, lower breathing mode. So it will be A1 prime. So the tensor element is this. Is this. Okay, so the Raman tensor will have a form of X, X, Y, Y, X, Y. Okay, because you have this, right? So that means you just copy the same thing that we have done. You just copy just the same thing. Copy. Okay, in this case, then this is not 0. Now this is 0. Okay, this is 0. Because you have this element that is in the tensor. So the -1 is not in the tensor, and it should be 0. Okay, so that means these are all 0. So that means this will be plus, plus. Okay, so that means these two are just equal. These two are just equal. Okay, so you can get the form will be A, B. Okay, so once you get this form, then you can easily show the Raman intensity. So I do it slightly quickly at this time. So you have 1, 0, 0. So you will become A, 0, 0. Okay, so that means Z.
I think this is Z
B
squared non-zero, not X1. Yeah, A1 prime is X squared plus Y squared, Z squared.
Oh, I see. Z squared. Okay, good. Okay. Yeah, good observation. Okay, good. That means you're listening. That's good. Yeah, why do I keep making mistakes? Okay. A, B. Okay. So very different. Okay. Then it's already obvious. It's a diagonal element. Okay. So that means whatever you put in, you get the same thing with a constant. Okay. So you get A11. So similarly, the same for X and Y. Okay. So if you put in what? If you put in the 1i, then you're going to get A1i. So that means if the incident light is plus, then the scatter light, the scatter is also the same. Okay. So from here, you can already see that You have x, y, y, or the sigma plus sigma plus sigma minus sigma minus, you are going to get finite Raman. However, if you put xy or sigma plus sigma minus, I mean, you can call this horizontal and v, or left and right. So just different names, okay? Different names. Then you're going to get 0. Okay. So you can call this horizontal, vertical, left, right, left. Okay, this is I mean, different paper use different symbols, but you know the meaning. Okay, so these are the selection rules. Okay, so now let's go to the last one, A2 double prime. A2 double prime is this one, and you can see there's no tensor element here. It's only Z. So this is infrared active and not Raman active. Okay, so ABA, higher breathing mode. It is A2 double prime, and then is Raman inactive. So this is a Z representation. Okay, then we're done. We're done with this row. Okay, we're done. Not that difficult, right? Just a simple linear algebra. Okay, let's continue on the ABC. Okay, let's continue on ABC. ABC has a D3D symmetry group. Then you just go to D3D. Here, D3D. Okay, you click here. Okay, then you see the character table. And then you just go one by one. This is EG mode. So EG mode. EG mode is this one. Okay. Then you can already see the character. You can already see. Okay, you can already see this. This is the representation, the tensor element that are finite for the EG mode. So let's continue. ABC trilayer graphene. So D3D. So let's say the lower shear mode. Okay, after we know that, then we can move faster this time. Okay, so this will be EG. So you can write down the matrix element. Okay, this one. XY. And then what's the next one? XZYZ. Okay, so that means you're going to have all of this. Okay, all of this. Then they're going to transform like this. So you can write them separately. So for this one, we know the Raman tensor will be, I mean, we already dealt with this form before, right? So I'm not going to repeat it. Okay, so once you see this, you know it will be A negative A. This will be BB. Okay, so I'm not going to repeat it. You know how to get this one, right? So for this one, then you just 0, 0, C, D, C, D. So these two are exactly the same as what I dealt with before. Let me just quickly show you. So for this one, you have this representation here. Then when you use this, then you get a form like this. Okay. So previously, for this one, you have this XZYZ. then you know this, then you just write it as C and D. Okay. So even though the name of the representation are not the same, but once you see the table, you see this matrix element, a tensor elements here, then you can immediately write the form. And then all the selection rules will be exactly the same. All the selection rules will be exactly the same. Okay, so both of these are true. So for this one, you can already see this one. You can see x and xy is going to be finite. Okay, then xz is going to be 0. And yz is going to be 0. And then this one will be, I think, the left and right. Left, right is going to be 0. And then it's going to be finite. Then for this one, you have x and y, x is going to be 0. xz is going to be finite. Okay, both. Both. Either one of this. Either one of this. Okay. Because this one means this phonon can become like this or like this. Either one is allowed. Okay. So that means the phonon will either behave in this way or behave in this way. And I don't think it is not the sum of them. Not the sum of them, okay? Because not the sum. Because once you sum them together, it's not a irreducible representation anymore. Okay, the Raman tensor is not like this. It's not like this. You cannot sum them together. Can you say, I sum them? Yeah, this is a representation, but this is not an irreducible representation. All the eigenmodes, they must be belong to one irreducible representation. So it's either this one or this one. So that means group theory cannot tell you which one it is. You need to go to the more details to see whether it is this one or this one. Okay, and I mean, you can use an experiment. If you don't know whether the phonon is this mole or this mole, then you just do a Raman measurement. You'll be able to confirm it. Okay, because both of these transform according to the same representation, and group theory cannot tell you more than what the representation can tell you. Is that okay? So just either one of this. And in our detection geometry, we confirm that it is this one. Okay, because we see it. Okay, because we see it. So it is not this one. Because in our geometry, we don't detect any Z. Yeah, if you see this, then it is not this. Okay. Okay, let's continue. EUIR. Okay, EUIR is simple. You have EU here. And then this is just XY. There's no tensor element. Okay, so we can quickly write it down. Just go through it one by one. Okay. EU. This IR. And Raman inactive. Okay, we're moving quickly. Okay, this is A1G. A1G. Okay, what is A1G? A1G is this one. Okay, this is A1G. Okay, so you have a This is higher shear mode. Lower breathing mode. So A1G. A1G belong to this one. Z squared. Okay, so you can see the form of the Raman tensor will be AAB. Okay, so you can immediately know the selection rule will be whatever you put in, you get the same representation. So you have X, Y, Z, Z, left, right, it's going to be finite. And you have X, Y, and left or right, you're going to get 0. You're going to get 0. Okay, then let's go to A2U. A2U is this one. You have a Z dipole and no tensor element. So this is going to be Raman inactive. Okay, so you have higher breathing mode. A1U is infrared. And Raman inactive. Okay, so then we're done. We're done. Okay, so you can write a summary. You can write a summary. How can I write it? Okay. ABA. I think I have something like that before. Let me just copy. Okay. Get this one. B. Okay, let's write a summary. Like this. Then you can have ABA. So from this, you can just write down the selection rule. I actually forgot. Okay, so let me write down the selection rule. The first one is sorry for keep going back and forth. Okay, this is XZ. Okay, this is XZ. This is XZ. YZ finite. All others, 0. Okay, the higher shear mode. The higher G mode is what? Let me see. Okay, this is the highest shear mode. The highest shear mode. The highest shear mode is this one. Okay. You just summarize. And then we have left and right is finite. I should write it like this. Left and right. And right. 0. Okay, so And then the lower breathing mode. So it's a bit tedious, but let's finish this part. Lower breathing mode is this. Okay, so this will be left, right, 0. Okay, I think that's it. And then this one will be Raman inactive, 0 for all of them. Okay, so this is 1, and then later, and let me just do the same thing for the trilayer graphene. So this will be the, if I remember, this is the EG, EU, A1G, A1U, A2U. Okay, this one will be easy because 2 of the mode are Raman inactive. So you just get 0 for this one and 0 for the other one. EG is this one. So, and here we only focus on this mode. We know it is not this one because in our detection measurement, we detect the light for X and Y geometry. So this is the mode. Okay, so I remember this one will be, this one will be X, Y is finite. And then you have an LR finite. And then we have LL and RR are 0 for this one. I mean, when you see this, it means you are going to flip the helicity. Okay, and if you see both X and Y, that means you're going to mix the X and Y polarization. Okay, then this A1G is just this one. Okay, this means it's a diagonal element. Okay, diagonal matrix. Diagonal matrix means, yeah, means just the same as this one. Okay, I think that's it. So these are the summary of all the Raman selection rules with the polarization. So you're going to deal with them one by one in your measurement. Okay, so now I'm going to show you some more results. This is only related to graphene. And unfortunately, in this paper, I did not have the polarization resolve measurement to show you this. But we did another work in MOS2. Okay, so I'm going to show you the result of this paper and show you the selection rules. Okay, so in this paper, this is the paper written by Jeremiah and me, and with the Professor Ruihi's group. Okay, so we're going to deal with the 2H MOS2. Okay, so we're going to deal with this. So for 2H MOS2, I think the group is D3H. Okay, D3H, because it says that 2H MOS2 has for odd and even layer number. Okay, even layer number is D3D. Okay, so for bilayer MOS2 is D3D. D3D. So we already have a D3D in our analysis because ABC trilayer graphene is also D3D. Okay, it's also D3D. D3D. So let's continue D3D. So in this paper, there's another paper from Professor Chun Hung's group in UMass Amherst. So this paper, they talk about helicity resolved Raman scattering of this 4 kind of TMD with different layer number. Okay, so in this paper, they did the helicity resolve measurement, and this is a character table showing you the groups and also the representation of different modes. If you're interested, you can read this paper. But today I'm going to only focus on the shear mode and breathing mode. Okay, so we're dealing with a bilayer. Okay, with a bilayer. So this bilayer has D3D group, and look at the shear mode. The shear mode is E2G, EG, and then the breathing mode is A1G. Okay, so let me just write it down. EG. Okay, so we're gonna deal with 2H MOS2 bilayer. So the group is D3D. Okay, so for bilayer there is only one pair of shear mode degenerates, and then you have the breathing mode. We call this S, and this is B. So what is the representation? The representation is EG. This will be AG. Okay, so let me double check. Okay, EG, A1G. Okay, A1G. This is A1G. Okay, D3D. Then let's go to D3D again. It's already here. Okay, A1G. You can write down the matrix form. And then EG is this. Okay, so I just write it down. Okay, these are the 2, but we're going to deal with this one because it turned out that when we make the measurement, we confirm that it is this form. Because when you shine the light and detect the scatter light, you see the signal from the reflection geometry. So from here, we just directly copy from here. Okay, so these are the okay, you see the same group, you see the same representation, then the selection rules are basically the same. Okay, so you just directly copy this one. Just directly copy this one. These are the selection rules. A1G is this one. Copy. Okay, so that means for this one, you're going to only see in left and right. On left and right, let me highlight it. This will be finite. And then this one, this is finite. Okay, and then this one, this is 0, and this is 0. So you can see that they have opposite helicity. Is okay? For this one, you have L left and right, you see finite signal. But for this one, you have a left and right, you see 0 signal. And for this one, you have left, right, you see 0 signal. For this one, left and right, you see finite signal. Okay, so they're going to change the helicity of the Raman differently. Okay, so let me show you the result. This is the result. Okay, I mean, this is the paper. So when you do right, you are going to see the breathing mode. When you use right-left, you are going to see the shear mode. Okay, so cross one is shear mode. Co-polarized one is the breathing mode, and you can see, this cross one is shear mode. The co-polarized one is the breathing mode. Is okay? So this can be done by the experiment. Okay, is okay. So now let's go to another paper. This is okay. This is our paper. Okay, this is our paper. For this one, we did not use helicity. We use horizontal and vertical polarization. So these are the results. I mean, these are two kinds of stacking order, but let's just focus on the 2H. Okay, let's focus on 2H. So you have the co-polarized linear polarization and cross-polarized linear polarization, HV. So let's focus on the bilayer. Okay, so I cut this out and put it in the PowerPoint. So this is the result. So you can see if you use XX or YY, or here is vertical, you are going to see both modes, shear mode and breathing mode. But if you use a horizontal and vertical, like cross-polarized, this is XY or YX, you're only going to see the shear mode. Okay, so let's compare this with our results. Okay, for shear mode, for XX and YY, you're going to see finite one. But for breathing mode, for X and YY, you also see finite one. That means if you use the XX or XY, you are going to see, okay, if you use XX, you are going to see both the shear mode. This shear mode is XX is finite, breathing mode XX is finite. So for co-polarized light detection geometry, you're going to see both. And this is what we see. We have a co-polarized one. You see the shear mode and you see the breathing mode. Okay. But if you use a cross-polarized one, you use XY, okay, then you are going to see the shear mode. But if you use XY for the breathing mode, you're not going to see it. It's going to be 0. Is that okay? So when you check the result, you use a cross-polarized one, you see the shear mode, but the breathing mode is gone. Is this okay? So experimentally, you can actually confirm it. You can actually confirm it. Okay. So of course, in the paper, they have many more results. For example, I mean, you can read the paper by yourself if you are interested. I'm not going to go through them again because the algebra is almost identical. Okay, so let me introduce something other than the shear mode. So in this paper, they also consider the optical phonon. Okay, they also consider the optical phonon. So here I in this PowerPoint, so this is a phonon band structure of bilayer MOS2. I copy from this paper. Okay, so when you zoom in, zoom in. So this higher one here is the breathing mode. The lower one is the shear mode. Okay, so these are the two that we consider. They're relatively simple. But when you go up to here, you have some optical phonon mode. If you see the twofold degeneracy, you know that the in plane vibrational mode because you have the twofold degeneracy. If you see the one, that is one mode. Those are the out of plane vibration. So these two are the in plane, and then these two are the out of plane. So these two are Raman active. E2G and A1G are Raman active. Okay, so these are the representation. So when you go to Chun Hung's paper, they consider this two mode. Okay, C means chalcogen, M means the metal atom, IC means the chalcogen atom is vibrating, and the metal atom is not moving, and it is in plane. In plane, IMC means both the metal atom and the calculation atom are moving, and they are in plane. Okay, so you have these two kind of optical phonon, and then you have OC. O means out of plane. C means the calculation atom. OMC means both the metal and calculation atom, they are moving out of plane. Okay, so these are the four phonon modes that you see here. So there are 1, 2, 3, 4. These are the four modes. Okay, these are the four modes. Then this shear mode, breathing mode. Okay, that's fine. Then you go to the table. Okay, they go to their table. Then you can see the IC mode, the IMC mode. Then you see these are the representation. Okay, these are the representation. Okay, and these are also the representation. Okay, so once you can see that. Okay, you can see that this mode, they have the same representation as the shear mode. The shear mode is EG. They also are EG. Okay, they also are EG. And then let me see. They have the horizontal plane. Okay, I think this probably means the. Okay, let's skip this part. And then the breathing mode, you can see this out of plane mode. They also have the same representation. They are all A1G. So once they have the same representation, then the symmetry property will be the same. Okay, then all those selection rules will be the same for the Raman. It doesn't matter how you vibrate, it's what representation you are determining the selection rule. So they will actually have the same selection rules as the shear mode. Okay, for example, you can see that this is the Raman shift of the optical mode, IMC and OC. These two, I think this is E2G mode. This is the A1G mode. These are the two modes that you see when you do the Raman for MOS2. But usually you see both of them together. When you shine the light, you see both of the peaks. Okay, but they follow different selection rules, and you can separate them. So how do we separate them? You use the helicity. Okay, this is the right detection. When you do the right detection, then you see this OC. Because for right detection, this one has the same selection rule as the breathing mode. Okay, the matrix, the tensor element is going to be diagonal. Okay, so you just get the same helicity with the incident light. And this IMC is the E2G mode. The E2G mode follow the same selection rule as the shear mode, and it is cross-polarized. Okay, so when you use left and right, you're going to see it. Okay, you're going to see it. So basically, these are the selection rules for those modes. They follow different helicity. Okay, and if you go to higher layer number, these are the higher layer number. You have monolayer, bilayer, trilayer, all the way. Then they also actually follow the same. You can actually derive this also from the selection rule. So if you go to here, this table shows that for odd number and even number, they have different symmetry group. And then these are the representation. You can see that for the shear mode, this is the representation. They all have actually the same representation as the shear mode. The same for the odd. This one has the same representation with the breathing mode for all the layer numbers. So basically, you get you understand how we derive the selection rule for shear mode and breathing mode. Then you can generalize it into the higher energy optical phonons. They just follow the same selection rules. Okay, so I'm not going to get into any of those details. I think it's just the same method applying to higher layer number, but eventually the result is just the same. The result is just the same. And if you go to higher layer number, then let me see. These are just different TMD, I mean, they're all the same because the symmetry property are the same for all four kind of them. So the result are all the same. Okay, when you go to tri-layer, 4-layer, then you're going to separate the breathing mode and the shear mode by using the helicity. Okay, and we get something quite similar for Jeremiah's paper. Okay, for Jeremiah's paper, when you use a copolarized light, you see both the shear mode and breathing mode. So these red dots are the shear mode. And okay, breathing mode. Okay, breathing mode is the red dot is shear mode, the breathing mode the blue one. So you see both of them for actually all the layer number up there. But when you use a cross polarized one, you only see the shear mode and for all the layer number. So then we use this tool to separate them. But in principle, if you use helicity, I think you can separate it better, just like Professor Chun Hung's paper here. Okay, so if you're interested, you can go to do the analysis for 3R MOS2. You just apply the same one for 3R MOS2. We already have the group here for you. Maybe just quickly do it. Then you actually let's do one more example. Okay, for this one, it's 3R MOS2 is C3V. C3V. Okay, so let's do it C3V. So for 3R MOS2 is C3V. The group is actually simpler. Okay, so when you go to C3V, then you go to here. C3V here. Okay, so the table is very simple because it's, the symmetry is relatively low. You can already immediately tell that this is the shear mode because the shear mode are doubly degenerate. There's only one two-dimensional representation. Okay, so from here you can already write down the element. Okay, it is this one. Okay, so let me write it down. For the shear mode, it will be x squared minus y squared xy. So this will be the E representation. So we can neglect this one because we know it is not this one. Because in our experiment, we use the XY geometry, we detect some signal. Okay, so it is not the other. For the breathing mode, it will be this one. Okay, because the breathing mode just vibrate vertically. So it vibrate like a Z vector. Okay, so it will be this one. Okay, it will be this one. So A1 mode. So the breathing mode will be A1. Okay, so you can already tell. Okay, so you can already tell because here you have this one, right? Okay, then you just directly copy the selection rule. Okay, I mean you can see that the representation name is different, but it doesn't matter. When you see the tensor elements are the same, this determines the form of the Raman tensor. So the form of the Raman tensor just determine. Then you just paste. Maybe I just write this way. This is breathing mode. Okay, so this is the selection rule, and okay, and this is the breathing mode. The same. Then you just copy this selection rule. Okay, you just copy this selection rule. Okay, so that means for the 3R mode, you have, we don't have the helicity thing. Okay, so you have this x, these two are finite, and then only this one are finite. The others are 0. So that means you use x, y, you're going to see the shear mode. You use xy. So that means if you use x, you're going to see shear mode and breathing mode. And if you use XY, you're going to see only shear mode, no breathing mode. And you can check our result. This is what we see. Okay, if you use XX, VV means that copolarized. You're going to see both shear mode and breathing mode. You use cross one, you only see one. The result is actually the same as 2H. You just do the analysis, it's just the same. Okay, so these are some of the simple theory of Raman related to group theory and some of our data derived from those selection rules. Do you have any questions? Okay, if no, then we'll end the lecture here. Thank you very much.